Okay, and so the last of our fundamental relationships is going to be the constitutive relationship. Constitutive relationship. Gotta make sure I spell that right. Okay, and what its job is it's going to relate stress to strain. So those are our two fundamental quantities. There are material properties, or quantities. And unlike our kinematics relationship or the equilibrium relationship, our constitutive relationship cannot be derived from basic principles. So as much as I'd like to draw a picture of a rod and we can work out what the relationship should be, in this case we can't. And so in order to determine these constitutive relationships, you have to do some testing. And as you know from your life experiences, different materials have different properties. And so we need to test each of these different materials to come up with these relationships. For a lot of what we're going to be doing in this class, we're going to make a simplifying assumption. And that is that most materials, if you don't press them too far, behave in a linear elastic fashion. And to think back on history a little bit, in 1676, there was Hooke, and he did, there's an E there, he did some tests on springs, and he came up with Hooke's law, and that was, again, a linear elastic assumption. And much later, in 1807, had a guy named Thomas Young who did tests on materials, and he found that materials behave in a similar way for modest levels of load. And so you'll often hear this relationship, which is stress is equal to a constant E times strain. You'll often hear this constant E referred to as Young's modulus, or the elastic modulus. It is a material constant that is obviously going to be different for every different material, but it relates strain to stress, and it's just a linear relationship. So I'm going to draw some axes here just to reiterate. If this is strain and this is stress, what we're saying is we have some relationship here that looks like that. And the slope of that relationship is E, the elastic modulus. So on this side, remember, we have stress, which is in force per area. That's on this side. We have this unit here, which is length per length. So that means, what's the units of our elastic modulus? That's going to be force divided by area. And so just again, E is the modulus of elasticity. Sometimes called Young's modulus, relates stress to strain. And this relationship is true for modest levels of load. And for many engineering applications, this is all we really need. So this is often all we need for engineering applications. And that's because we design our engineering component, our part, or our piece of a structure to be elastic under the applied loads. And just to talk a little bit about materials, some different materials here. So I want to make sure that you can see here. So the elastic modulus is material dependent, and I wanted to just give you a few kind of values here for some different materials. So aluminum, E is about 10,000 KSI, or 70 gigapascals. Steel is going to be around 29,000 KSI, or about 200 gigapascals. Concrete, since I am a civil engineer, concrete is going to be about 4,500 KSI, which is about 30 gigapascals. And if you go all the way down to rubber, pretty stretchy stuff, rubber has an elastic modulus of about 0.1 KSI, which is about 0.7 gigapascals. And so that, hopefully you can see all those. So that just confirms what you already know from your life experience, right? Steel is much stiffer than rubber. You can stretch a rubber band. It's awful hard to stretch a paper clip.